Here is your bell ringer for the day. Please read this. Okay, take some time to read this, and then I'll scroll down so you can see the points here that you're going to need. All right. Actually, you guys have this on your sheet. You have a handout, so you can go ahead and read it and try it first. Okay. So going through this, did you know that in 1776, when the Constitution was written, there were 13 stars on the American flag for each of the 13 colonies? You should learn that in history class. The number of stars grew as time went on. Below is the table of the data for the number of years after 1776, the number of stars on the flag. What type of function best fits this data and why? Write the correct algebraic equation for the function. Okay, based on your equation, how many stars should the flag have in 2014? So you guys should have put this in your calculators, and you should have done a regression of all of them. Okay, and you might have that on your notes actually for what the regressions are. Okay, so if you see those on your note sheets, you have linear is 0.9376, exponential is 0.880, and power is 0.7345. Okay, so this is the equation that you wanted to use, your linear equation. So whatever you got for your y equals mx plus b on that one. Okay, because that's the best one. All right? I don't have this one worked out for time's sake, but you guys should have the equation that the calculator gives you for your y equals mx plus b. It gives you m equals something and b equals something. Okay, so you're going to use those values, and it says how many stars should the flag have in 2014. So you're going to find years after 1776. That's what you're going to plug in for x. And then you should get your answer, whatever that is. Okay, so please share with each other, see if you guys got the same answer on that problem. All right. Second slide is just another slide of all the data. Okay, since I printed it off for you guys, I don't really need to go through that. But 8.4 is what we're doing today, and it's going to be a little different because we have different types of graph paper now in pre-calculus. All right, so we are linearizing data and logarithmic graph paper. Okay, so I want you guys to start with the exploration. The stuff can hand it out to you. It's exploration 8.4a. The answer key is on the front desk, so if you guys need to check it out while you're going through that, it's up here. All right, so take about 5 or 10 minutes, see if you can get it done in 5 or 10 minutes, and compare answers. The key is also on the sheet that you guys have, the handout, so you can check your answers there too if you need to. All right, so take a few minutes to do that. All right, so if you were working through that 8.4a, all right, it wants you to give you a set of points for each of the problems, and you need to find the particular equation for each one. All right, once you found those equations, it has you plot the points on the graph paper that you're given. Okay, and the graph paper should look similar to that stuff right there. All right, so the first one that we're looking at is log graph paper. Okay, so what that means is that there's a logarithmic scale for the x, and there's also a logarithmic scale for the y. Okay, this stuff here is important. So you want to make sure that you highlight that if you need to. Okay, something to look at on your notes. Okay, and you're going to want to add points to these graph papers on the side here so that way you can use it. Okay, so log is used for power functions. Okay, and what we use this for is linearizing power functions and logarithmic functions. Okay, it's kind of cool once you start plugging in points because power functions normally look something like that, right? And it goes through 0, 0. So now we're going to turn this kind of power function into something that looks more like that, like a straight line. Okay, so on the graph paper here, you're obviously going to start in the corner with 0, 0, but then you see a different scale going to the left or going to the right and going up. Okay, this would be 1, 2, 3, 4, all the way up to 10. Once it crunches together, that dark line there is a 10. After you get to 10, then it starts going by 10. So it's 10, 20, 30, and then it gets up to 100. Okay, so that's the pattern. So you can kind of see that. If I'm looking here, I'll go up to 10 here, and I'll go up to 100 here, and then it just goes by 100s after that. So you go to 1,000 up there, okay? So you'd be plotting points on there specific to the equation that you're given. Okay, and we'll do some of these in a little bit here. All right? So that looks like the log, the way you can recognize it's a log function or a log graph paper is it kind of gets crunched together when you're going to the right, and it gets crunched together as you're going up. All right? This is for a multiply pattern, okay, which is right here. And if you guys remember, multiply is for power functions. Okay, so that's specific to power functions. Okay, the next type of graph paper is semi-log graph paper, and there's actually a couple of these. Okay, there's a couple different types of semi-log graph paper. This first one that we're looking at is used for exponential functions. Okay, and if you remember exponential functions, the pattern is add, multiply, all right? So you add your x's and you multiply your y's, all right? And it has a logarithmic scale on the vertical axis, okay? That would be your y. So that's a log scale on the y. And then it just has the normal scale on your x. So that's your add. So if I'm thinking about my scale on my x here, okay, I'm going just doing normal there. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Next, and then we're going up. We're going up in a logarithmic scale. So that bold line there is going to be a 10. That next bold line there is going to be 100. That next bold line is going to be 1,000. Okay, and it keeps going up. This would be 10,000s. All right. So that is for exponential functions because their pattern is add, multiply. So you got to think. Another way to recognize this is you're going to do add for x and multiply for y. So x is going to be the normal scale, and y is going to be the log scale. Okay, it's specific to the pattern. So you guys got to memorize those patterns again for the different functions that we used before. All right, and the other type of semi-log graph paper is when we have multiply add. Okay, and if you remember, since exponentials were add multiply, these are log functions. Okay, so now we're actually using log functions on log graph paper. Okay, but we can do all these different functions like power functions, exponential, log functions. We can do all these on graph paper, but we're linearizing them. So it's multiply add, semi-log graph paper. You could just call it semi-log graph paper if you wanted to, and you could call it logarithmic semi-log graph paper. Okay, but the thing to notice here, since we're doing a multiply add, multiply is your x, add is your y. All right, so if you're thinking back on that last one that we just did, your y scale is going to be normal. So that's 1, 2, 3, 4, 5. And then your x scale, that's going to be your logarithmic. Okay, so your dark line here is a 10, dark line here is a 100, dark line here is a 1,000, and then dark line there is 10,000. Okay? So make sure you guys are adding little notes here, that way you can have something to reference. I know that I have these bullet points written for you. I still want you to add notes, that way you got something to look at later on. Okay? So, for the first example, we're going to calculate the y values for the given values of x. So x equals 2, 4, 6, 8, and 19. Okay, so I would make a graph or a chart for that. And so we got x there, y there, we got 2, 4, 6, 8, and 19. So go ahead and see if you can find those values for that. So if I had 2 into that function, okay, first of all, remember what kind of function this is. That's an exponential. Oops. Exponential, so your pattern for exponentials are add, multiply. Alright, so let's get our points here. So I plug a 2 in. We get 288. I plug a 4 in. We get 103.68. And I plug a 6 in. 3248. We'll just use all the decimal places we got here. Plug an 8 in. Get a little bit more. And plug a 19 in. And we got 0.048748. And we'll just do 8. Okay? So those are our y values that we got. We're going to plot them on the appropriate graph paper. All right. So I should have a graph that pops up over here. Yep. So looking at this, we have our normal scale on the bottom. That's our x, and then we have our log scale on the y. So if we plot our points, we got 288. All right. So the one thing I forgot to mention earlier is if you're doing your add pattern, really it starts at 0 for your add pattern, and then for the logarithmic pattern it starts at 1. So it's really the same point, but for your normal scale you start at 0, for your log scale you start at 1. Okay, so if we started here, we got 0, 1, 2, and 288. So remember that this would be 10, this would be 100, so that means this is 200, because we go by 100s after we get to the 100 line. So 288 is going to be right in there-ish. And then 4, 103.68. So 100, 103.68. And then 6, 37.3. So 10, 20, 30. So 6, 37.3 is going to be in there. And 8, 13. So it'll be 10. 13 is going to be in there-ish. And then we got 19, and we're pretty much about 0. So 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So it's out there. And that one doesn't look like it lines up very well. But if we do our line through there, this should really be what our line looks like. I'll have to adjust that a little bit. Make it skinny. And then we'll see if we can hit these points. Alright, so that's going to be our linearization of that exponential function. So that's what our graph will look like. Okay, and I might be off a little bit on the bottom, but that's about what you want it to look like. Okay, so for the next one, we are given a graph. So write the coordinates of the points given, write the appropriate regression equation that fits the data, find y of 2. Is it on the graph? Okay, so when we're looking at this, we have to find some nice points. And it's hard to see on the projector, so I'm going to kind of use my paper here to see it. But you're going to be looking for, that's my dark line, so this is 5, 6, 7, 8, 9, 10, and I got 20, 30, 40, 50. Okay, and we got the same thing on the other axis. So it's going to be something like that. All right, so what you're going to want to do is you're going to want to find nice points on your graph. So that way you can kind of get an idea of what they're going to be. So the first one I'm looking at is if I go by my 2 down here, and I follow that up to where it hits here, that point right there looks to be a little bit past 100, or past 200, sorry, because those go by hundreds once you get to there. So I would say that that one is going to be, I'm just going to make a chart here and record my points. So 2, about, we'll say 215. Okay, then looking for another decent point. If we go to 2, 3, 4, okay, so we're going to go to 4, and we follow it up, and it looks like we're hitting about, that's 50, 60, 70, 80, about 85. Okay, so 4, 85. So we're going to keep looking for good points. I'm just going to jump to 10 here. If I jump to 10, well, when I say good points, it's kind of subjective because I would say you want to look for points that are maybe a third of the way past the line or maybe halfway past the line. Or if you get some that hit right on the line, like that first one that we got, that 215, that's kind of close, but you got to estimate. Next one I want to go to is 10. So if I follow 10, I'm going to be about 10 for my x and maybe 27 for my y, 27, 28 for your y. Okay, if I go to 20, 20 looks like a okay point, so 20 is going to be about 11. And then I keep following out, let's look at 50. So if I look at 50, it's going to be at about 3. Okay, 50, we'll say about 3 1/4. Okay, now what you're going to want to do is you're going to want to plug those values into your calculator. All right, so we got A, right coordinates of the points given, and in the book you're actually going to have points that are written on the graph. Okay, so it'll be a little bit easier to see it, but you can write them on the graph when you were looking at. When I added these on the side here, I probably could have plotted the points. It's just kind of hard for me to see it on the projector. But write the appropriate regression equation that fits the data. So what you're going to do is you are going to put those numbers into a list, okay? And then you're going to get the proper regression equation. All right, so go ahead and do that right now. And I'm going to do it while you guys are doing it. So you don't necessarily need to pause the video here. All right, so if I plug those in, I do my regressions, my linear regression, I get about a 0.414. Okay, that one's definitely not it. If I do a logarithmic regression, I get, okay, so that's ln, I get 0.7782. For my r squared. So let's do another one. So exponential, we get r squared is 0.838. So that's our best one so far. And then we do power. Let's see what we get for power. Boom, that's it. So we get 0.99987. That means that's the one we're going to want to use. All right, so we look at the values that we're given. So we have A times x to the b, that's our power function, and it tells us that our A is 524.814, and our B is a negative 1.296. And the more decimal places you get with this, the better off you are. I'm just kind of going with it here. All right, then the last one for part D, so we got A and B, it should have been A, B, C. Find y of 2. So that means we got to plug 2 into that function. All right, so you got 524.814 times 2 to the negative 1.296. And 2 is about 213.7, which is pretty close to what we had here. Okay? We're 213.732. Okay, so that's pretty close. Not too bad. Just looking at those points. That's what you're going to have to do in the book. All right? So make sure you guys got those notes down for this one. All right? So we got 2 more things here. And then you're going to write down a generalized pattern, and then you got some homework. All right? So looking at the next one, linearizing exponential functions. So we could use our graph paper to linearize these, but there's an easier way to do it to actually find an equation. All right, so looking at these, we want to linearize exponential functions. So the way we can do this, you could look at the next page if you wanted to. I'm going to write it out. I want you guys to write it out just to kind of get practice and see what it looks like. But I would take the log of both sides. So I take log of y equals log of 20 times 1.45 to the x. Okay, now you got to use properties of logs. How can we split this up? All right, well, since we're multiplying inside the logs, what can you do with the stuff inside the logs? We can break it up into 2 separate logs and add. So I got the log y on the left here, and I'm going to split these 2 up on the right. Okay, so I got log of 20 plus log of 1.45x. And you should kind of see some things happening here. Log of 20 is just a number. Log of 1.45 here, I can't do anything because I got that x up there. But with our other properties of logs, we can bring the x out front. All right, so that's the next step. So I have log of y equals log of 20 plus x log 1.45. So now I have just a number there and a number there. So our final equation is going to be about this. So I got log of 20 is about 1.3010, okay, plus, and I'm going to put my log of 1.45 out in front, so 0.1613x. I'll add a couple dots there, say it's a continuing decimal. All right, so think about y equals mx plus b here. My slope is that 1.0 or 1.301, and my backwards, the slope goes by the x. That's over here. That's my slope. And this one is my y-intercept. So really, you could graph that. If you look on the next page, I have graphs of that function there, or not the next page, the next slide, I guess. Okay, this would be my y-intercept. That's going to be your slope. You could put that into a calculator, just normal like that, and it would graph you a line. Okay, so looking at this is the same. These are the same steps. All these. That's what I wrote down with pen. All right, but looking at the two graphs, you got our exponential there on the left. Okay, exponential on the left there, and we got, our linearized power function, or linearized exponential function, sorry. This one over here on the right, that is the linear form of that exponential function. Okay, kind of cool, you can change one exponential into a straight line. Okay, last example here. So linearizing power functions. All right, well, think about how we just did it with log functions. We're going to do the same thing with power functions, but we still have to use different properties of logarithms. Okay? Well, it's pretty much the same properties here. But we're going to start out taking log of both sides again. So I have log of y equals log of 60x to the 3.45. All right, so think again. How can I break this log up? I have log of y equals log of 60 plus log of x to the 3.45. Well, remember, here, log of 60 is just a number. 3.45 comes out in front. So our next step, we got log y equals, I'm going to write in the decimals here. So log of 60 is about 1.7782. And then we have 3.45 log of x. Okay, so you might be thinking to yourself now, well, I have a log of x. Before I just had a regular x. Well, why do I have a log x? All right, well, that's good. We want it for linearizing power functions because if you think about the pattern for power functions were multiply, right? Think about at the beginning of the lesson here what kind of graph paper we used for a multiply pattern. Okay, that was that log graph paper. And I'll actually go all the way back to that so you guys can see that. See if I can find which one it is here. I think it's this one. Yep, so when we're looking at power functions, we have a logarithmic scale on the x and a logarithmic scale for the y. So that makes sense that we actually got a log x in there and a log y in there because when we linearize it, when we put it on the graph paper here, you got a log scale going left and right, you got a log scale going up and down. So that's good. That actually means we did it right if we end up with that. Okay, so if we think about just making this an equation or writing out the equation for this stuff right here, that's my y-intercept. And then that stuff right there, that's my slope. Okay, so same thing as in the last one. If you look on your next slide there, you have the graph. Okay, you got all the work that I did up there, same kind of deal. And then you have your power function graph there. So that's good. And then we turned it into a linear graph right there by linearizing with this line right there. Okay, so kind of cool. So the next slide here is just kind of in general, linearizing exponential functions. So if y equals a times b to the x, then you want to take the log of both sides. Okay, it'd be, or this is generalizing, so you don't need to do all that work really. So you take the log of both sides, so it'd be log of y, and you're going to have log of a plus x log b. All right, and it might be easier just to memorize the process of linearizing versus the process, or just memorizing this. Okay, so if we're looking at the first one, so that's exponentials. Second one, that's power. Okay, same kind of process. Okay, for power functions, it says if y equals ax to the b, then log y equals log a plus b log x. So that's where we got that log x in there, which makes sense because it's on log power, or multiply log paper. Okay, so kind of something new. Make sure you guys practice this. All right, you're going to have to memorize how to do this for the test. You're going to have to graph on log graph, or you're going to have to graph on logarithmic graph paper on the test. All right, so make sure you guys practice it. So there is your assignment, and I have a handout for you guys to do the assignment on. There should be 4 different graphs, and I think it's the correct graph. If not, you might have to draw your own, but I'm pretty sure I have it correct on there. So email me if you guys got questions. Good luck.